We're going to look at arc length here, and this is calculating the length of a curve. So first we want to define arc length, and there's a lot going on here, so we'll walk through it piece by piece. Integrating a function calculates the total change. So it means that positive and negative changes will cancel out. And sometimes we don't want that to happen. So for example, if you walk to store and back and you integrated your velocity function, you would get a net change of 0 because your net change in position is 0. You go, 10 meters that way and then come 10 meters back. Obviously, if you're going to the store, it's probably farther than 10 meters, but you get the idea. You do some change one direction, you undo it going back the other direction, it all cancels out. And that means if you wanted to know that total distance you traveled, you can't just integrate it, because integrating this, your velocity function would give you a change of 0, because you didn't move between the start and end. You're back where you started. So this is where we talk about arc length. Arc length will give you kind of only looking at adding it all together. It won't worry about whether it's positive or negative or stuff like that. So 1D arc length, if you just have a line going back and forth in one dimension, this is most commonly used for distance traveled when referring to motion. And the way that we would do that is just the integral from a to b of f of x dx, but we make this absolute value. Because if you're just going back and forth, we want to make sure that it always just gets added together. So if you go 5 meters this way, but then you come back by 3 meters, we want to add that 3 and get a total of 8. So that means instead of this being a negative 3, we want to make it positive 3. And that's why we just throw these absolute value signs on there. The way that you actually end up doing this is you just then look for anywhere that this function is negative, you just force it to become positive. So anywhere that this would be giving a negative change, you make it a positive change. This is something that it's a little hard to wrap your head around, but when you actually go do some practice problems, it should click into place, or ask me and I'll help kind of cover that and clarify things with you. Two-dimensional arc length is a little bit different, and this is where it kind of gets a little bit involved. So more commonly, we're going to be looking at 2 or more dimensions. So you're not just going to have a particle moving back and forth like this. You're going to have it moving through space and time, right? And so now this is a little more complicated, because how do you actually calculate the length of this curve? And it's functionally like laying a string along that curve and then straightening out. To measure it. So if you rolled out something along this whole line here, or you measured each little tiny bits along that and added them up, what would you get? So it's not just the x displacement, it's not just the y displacement, and it's not even the Pythagorean combination of those displacements. It's all of the ups and downs, and if there was loops and crazy stuff, it would be more than just the comparison of the start to the end. It's all the stuff in between. So let's look at how we derive that. So what we're going to do is we're going to start with a small chunk of the curve. So imagine this curve was continuing off, like this. So now for a small chunk of the curve, we can imagine a delta x and a delta y, right? And this hypotenuse right here is an approximation of this blue line here. And if you imagine getting smaller and smaller, the hypotenuse will get closer and closer to this blue as these x and y's get smaller. But for sake of just kind of starting with big picture, we're going to start by looking at one where there is a clear distinction, so you know that we're not actually technically calculating the blue, we're approximating it. So we're saying that this line, this red line I've drawn, the hypotenuse, is close enough to this blue line. And if we wanted to get a better approximation, we just make these delta x's and y's smaller. So if this right here, this blue line, we're going to call that delta s for arc length, because typically with arc length we'll use s. So delta s is going to be equal to, or it's going to be approximately delta x. Let me rewrite this where I have some more space. Give me a second. Clear that out. Okay, delta s is approximately the square root of delta x squared plus delta y squared. So we're starting by just saying it's approximately this hypotenuse. Now I can factor out a delta x squared. If you're not sure why I'm doing that, don't worry, it'll become clear later. But if I factor that out, that means I get the square root of delta x squared is delta x, so I can pull it out of the square root. And I'm left with 1 plus delta y squared over delta x squared. So I basically divided both of these terms by delta x squared to factor it out, and then I pulled it out of the radical to get this expression here. And that can be rewritten as delta x is equal or times the square root of 1 plus delta y over delta x squared. So in other words, we can approximate delta s as being basically equal to this length times the square root of 1 plus this length divided by this length squared. Now, if I wanted to make this more and more of an accurate estimate, I'd make these intervals smaller and smaller until I eventually get infinitely small, infinitesimally small. I get differential terms. So I get this ds, and since I am now infinitesimally small, these actually become equal because I get to such a small difference that this delta s becomes linear and they actually match. And this is just that kind of weirdness of dealing with infinitely small values. We can now say they are equal. And that means just all of these become deltas instead. Or not deltas, they become differentials. And suddenly this starts to look a lot more interesting. If I want to find the total arc length, well, then I just integrate both sides. The integral of ds is equal to the integral of square root 1 plus dy over dx squared dx. The integral of ds will just be s, and that will equal the integral of the square root of 1 plus dy over dx squared dx. And dy over dx, you'll notice, is just the derivative of y with respect to x. And so if you take 1 plus the derivative of y squared, square root that, and then integrate that function, you end up getting the arc length. Another way of expressing this, if you want, is like so. 1 plus f prime of x squared. And notice it's the derivative and then that is squared, not the square, or it's the square of the derivative, not the function squared derivative of that. So that's in 1D, or that's in 2D if you've got functions y as functions of x. We're going to look at parametric really quick because that's actually easier. It's the same as 2D, but the benefit is x and y defined independently. So it's one less step, and it kind of is actually easier potentially to see what's going on. So same idea as before. We've got our estimation, so I'm going to just jump straight into it. We're going to say ds is equal to the square root of dx squared plus dy squared. So I'm jumping straight to differentials as opposed to starting with deltas, but the same idea, it's just really tiny deltas. Then we have ds is equal to dt over dt, because remember, we're going to have functions x of t and y of t if we're dealing with parametric functions. Square root of dx squared plus dy squared. And then ds is equal to dt times the square root of dx over dt squared plus dy over dt squared. And there's no dt, integrate, and we get s is equal to the integral of the square root of dx dt squared plus dy dt squared times dt. And then the reason that this worked, again, is if I want to put this 1 over dt into the radical, I have to square it. So if I square, because 1 over dt is the same as 1 over square root of dt squared, if I bring that in, then I can distribute it, and we get this. And you'll notice this basically is just the Pythagorean theorem with the derivatives. And that's why this is kind of easier in a sense, at least to remember. Another way you could express this if you prefer is it's the integral of x prime of t squared plus y prime of t squared. And this is for parametric functions, and it'll also work for a vector value function. And that'll give you, the length of some curvy line defined with parametric functions. So that's the last thing that we have here for arc length. We'll go ahead and jump into the next topic next time.